하겠습니다.
Let's start this on the clock. Today's topic is quantifying the energy landscape of high-dimensional systems by diffusion decomposition. And let's start from reading abstract. And what's the case sentence?
Although
This part. So it's challenging to accurately quantify the landscape or high-dimensional oscillatory system. We are studying how to quantify the landscape in the high-dimensional oscillatory system. Usually, do you have any opinion or comment about this abstract? If not, let's move. The first, the energy landscape theory has been proposed to study the global stochastic dynamics of complex biological oscillators. This is the example of a cell cycle, one of the example of the complex biological oscillators. Cell cycle is some period with the same linear tickling, and they consist of the many components. So each model contains very many variables. So to study global dynamics, this system, we can utilize the energy landscape. The energy landscape is defined as the log of the probability density of at the steady state. So it looks like this. So by its definition, so by the property of a log function, the low probability at the steady state is the high energy. So this physically means that, so when some state has low energy, it is stable, so its probability in some state there in the steady state is high. So for example, in this landscape example, some stable place forms some limit cycle. So we can how the system is via the energy landscape. The question is that what quantify this energy landscape? So by definition, to quantify the energy landscape, we should quantify the probability density at the steady state. But in the multiple stable system, there are multi-stability, so its distribution is multimodal. So one of the approaches for constructing the energy landscape in the multi-stable system is using the weighted summation of Gaussian approximation. We can approximate the multimodal distribution with weighted sum of Gaussian, and if we take the minus log, we can calculate the landscape, energy landscape. this is the widely used method. So, yeah.
Question. At first, so we are dealing with oscillator system.
Yeah.
Can we define steady state?
No stasis. There is a steady state. But after time goes long, you can define the steady state, but rather than steady state is stationary distribution, and then because it is a limited cycle, it's not. So some flux exists, but we can calculate probability as after taking long time. If we send time layer to the infinity. Oh, there's the example in the next page. So to see how to approximate the stationary distribution, So we can see this example of a stroke of the oscillators. Or some stochastic oscillatory system can be generally formalized like this. So I will explain step by step. This term is the white noise. It is in the oscillator. It is this part. So this system is perturbed by Gaussian noise, and this F is the force. In this example, the F is here. If there is no noise term, it is same to just the ordinary differential equation system. So F is determined how the system is drifted by the dynamics. So F is the drift force, and G is the diffusion force. Because G is multiplied to the white noise term, it determines how noise diffused. So that's why it is called by the diffusion force. So if we take I will omit the detailed proof, but if we take some SD stochastic differential class, this form of the stochastic system can be formalized by this Fokker-Planck equation FP. So it is the equation about the station or equation about the distribution, quantifying the probability that state x at the time t. And from this equation, because this is the distribution of x and t, by multiplying x and taking integration, and then by applying some approximation, we can induce some equations for the first moment and the second moment. So by solving this ODE system, we can quantify the mean and first moment and second moment of Gaussian distribution. So let's use this equation in our example. First, this is the equation for the first moment. So intuitively, if the first moment is mean of the some population, so it is similar to the case when there is no noise. So it is same to just solving the ODE equation without noise. So, and the solution of this system is well known. It is the limit cycle forming the perfect circle with the radius of 1. So it can be parameterized. So mean equation can be parameterized by t, like this, cosine t by t. And then to get this equation for the second moment, we should calculate the Jacobian of F at the mean mu. So the Jacobian matrix is defined as the first derivative of the first element by the first variable. So if we calculate the derivative of this equation with respect to the first variable x, we can get this equation. And this part is derivative of this equation by y, and this is the derivative of this equation by x, derivative of this equation by y. And then if we substitute x and y to the mu t, then we can also get the equation parameterized by the t about a. And then in this case, in this simple example, the mu is independent of a t. It is just the identity matrix. So B is just an identity matrix. So if we substitute A and identity matrix are here, we can get the equation for the second mode. This part is just changed to the E2I multiplied by the diffusion coefficient. And then for the convenience of the calculation, we will transform the coordinate system, which consists of bases, tangential vector, and normal vector. We know that the solution of this system is the unit circle. So its normal vector is same to the its coordinate. So it is the cosine t, sine t. And we know that tangential vector is minus sine t, cosine t, because it is a circle. So let's go back to the linear algebra class. To get the transform matrix, well, the Euclidean coordinate system to the some system we want, we should multiply. Its transformation matrix is the consists of a column of new vector, new coordinate vector. So the transformation matrix is the normal vector, comma, and tangential vector. So let's change the coordinate. So to change the coordinate of a second moment, we will define new second moment by multiplying q to the both sides of original sigma. Then the derivative of mu hat is changed what mu hat is, so we can substitute mu hat by q transpose sigma and q. By the chain rule, it is changed to the sum of the one of its terms, derivative of its terms. We know the q and we know the derivative of sigma, so we can easily calculate this by taking some time. Then we can get the equation for the mu hat. Because we changed the coordinate, there is no some t related terms here.
Sorry, what is the D?
D is the came from the definition of came from the here, the second moment equation. It comes from this Fokker-Planck equation, the representing the diffusion coefficient, how to do it diffuse. So this comes from here. So to solve the equation for the second moment, we we usually write sigma hat is like explicitly like this. Then we can substitute to the system and we can calculate, or we can get the full ordinary differential equation system. So if we solve the first component ordinary differential equation about the first component, because the derivative of sigma 1 is decaying exponentially by -4, and there's some constant terms. So when time goes to the infinity, it goes to the d/2. So like this, we can solve the every differential equation easily, and it decays exponentially, power over 2 and power over 2, it decays to the 0. But the problem is that if we see the first component, sigma 2, there is no negative terms. So if we solve this differential equation, it is 2d times the time plus some constant term. So when time goes to the infinity, this does not decay. So it shows some explosion. So it makes the calculation, when this occurs, it makes the calculation inefficient when we apply the WSG, the weighted summation of Gaussian approximation. So then to solve this problem, we should know why does such explosion occur. Yeah.
So the mean, the body of the mean and mu and sigma is derived by assuming that the solution equation is Gaussian.
Gaussian, yeah.
Just simple Gaussian.
No, just simple Gaussian for each model. So if we use a multi-modal system, we should solve the multiple Gaussian, multiple of this system of equation. But this system is the unimodal system. So it just follows this one of the first and second model system. But if it is the sum of the Gaussian, if it is bimodal system, we should solve two of this kind of system for each Gaussian.
There is also some way to derive that the more body from the
Yeah.
instruments of Gaussian.
Yes.
Maybe you completed first moment, second integral of x.
Yeah, integral of x times. Actually, this equation derived from by multiplying x and integrating. But we need some approximation to small noise or large.
If you assume that the solution is Gaussian, then just knowing the mean and variance is enough to get the distribution. But if it's not
Gaussian, maybe
Gaussian,
it does not approximate it.
right, then it's not enough. And in this approach, we just assume that the distribution is Gaussian, multiple Gaussian.
Yes.
For each Gaussian, we derive this only for mu and sigma. So, but that causes the issue that the gap sentence here is that can cause a problem.
Yeah.
And that is the law of some.
Yeah. Some in some special cases. So this is the special case. And to see why this explosion occurs. We will derive this 2 by 2 matrix OD system as the 1 by 1 vector form system. For all the covariance terms converge in this system, the matrix should be consist of or should be consist of the negative eigenvalues. But the problem is that, as you can see, the false eigenvalue is not the negative. It is the 0. And this 0 is associated to the eigenvector is the tangential vector. So this stability condition comes from the local probability derived from the Jacobian matrix. But the limit cycle is the global property of the system. So the weighted sum of Gaussian approximation assume the stability of the system, but when the zero eigenvalue exists, the direction of tangent. So when the covariance of the noise diffuse to the direction of tangential vector, the limit cycle exists, but it cannot. Yeah, that's why the Jacobian matrix.
So here the law is that because this is tangential vector, that means we don't know the exact position of the system at time t.
Yeah, we don't know.
So if the steady state, the meaning of that constant variance means that over vector direction you can find some boundary or region that the system is placed.
here.
지금은 원원 방향으로 지금 양수, 그러니까 파이나타임에 한 따르는 거예요. 그러면 저 도말 벡터 위치 안에서 도말 벡터 방향으로는 열에서 나오는데 탄젠션 방향으로는 포함되어 있는 거예요.
그렇지.
그 말은 원 안에서 어디 위치인지 정확하게 모르는
이 시스템을 끌어당기는데 탄젠셜로 발산하기 때문에 영향을 안 주고 리밋 사이클 만드는 거라고. 다른 이제 네거티브 네거티브 스펠 리밋 사이클 탄젠셜 방향에 영향을 안 준다.
영향을 안 준다.
그래서 조기선을 발산해 준다. 근데 그런 걸 캡처할 수가 없어.
아 그러면 이거는 어프로시메이션 때문에 나온 거예요? 아니면 원래 시스템인 거예요?
이 시스템 원래 그런 거지. 영의 아이겐밸류를 포함한 시스템이니까 이 방법론을 적용했을 때 발산을 버리는 거지.
그러면 어프로시메이션 때문에 생긴 게 아니라 이 시스템 자체에서 이렇게 포뮬라이즈를 하면 어쩔 수 없이 이렇게 생기기 때문에 이 방법을 쓰면 안 된다.
맞아. 근데 이제 ODE를 푸는 방법이 발산하는 ODE를 풀기 때문에 문제가 생기는 거예요. This problem is of course because the weighted sum of Gaussian approximation.
So my point is that the diverging sigma 2 is not due to approximation, but it's the property of this system.
Yeah, right. But because this approximation apply the mass will solving the ODE equation diverging, so it makes an inefficiency and inaccuracy in the simulation. So to avoid this issue, the new method called by the diffusion, decomposition Gaussian approximation DBGA to decompose Gaussian noise into the decompose the Gaussian noise orthogonally along the tangential direction of the limit cycle and n-1 dimensional normal plane. So original noise can be decomposed to the tangential direction to the which is the orthogonal to the limit cycle and normal plane direction. So first, if we decompose system to the into the one-dimensional noise, one-dimensional variance term and dimension and n-1 dimension, then first we can solve the and these two are independent, so we can solve independently. And if first we apply the Fokker-Planck equation to the first dimensional system, it is on the limit cycle. So there is no flux in the probability distribution, and complex Planck equation is just switched to the simple differential equation system. So the advantage of this is that we can explicitly solve the system. So you can calculate the distribution of the first component like this, and record calculation. This solution is the pre-solution. So we calculate the probability distribution of the first component and make some divergence to the tangential vector can be solved exactly first. So after decompose this, we can solve the n-1 dimensional equation. So before we calculate to solve the system, we should make the orthogonal basis V2 and from the Vn, the n-1 dimensional basis. So for this, we can use the Gram-Schmidt to the V1 and n-1 Euclidean basis vectors. So maybe everyone learned the Gram-Schmidt in the linear algebra course. That's our end of the explanation. So we can make a n-1 dimensional Euclidean system. Then, as we did, if we make some transformation matrix consist of column vector of the new orthonormal relations V2 and Vn, we can transform the original coordinate to the n-1 normal plane system. Then, after that, at the limit cycle, still there's no additional flux to the probability distribution, and we can switch. Sorry for the typing. The Qt type the mu hat and Q. Instead of sigma, we can switch we can substitute original sigma to the Qt times sigma hat and Q. Then by solving this linear algebra equation, so just algebraic equation instead of the ordinary differential equation system, we can calculate the n-1 dimensional variance in the normal plane. So after getting the covariance matrix from these two variables, n-1 dimensional and tangential vector dimension, we can merge them just by using the weighted sum of Gaussian term. And each variance is defined as the change of coordinate and the sum sum of the previous direction, the diffusion to the previous direction. So they apply this new method to the synthetic biological oscillator, followed by the diffraction later. It is the typical example of a synthetic biological oscillators. So three components repress each other, and because repression of repression is the positive feedback, it forms the negative feedback. And there is some Gaussian noise. And if we apply each previous Gaussian approximation method, this is the ground truth calculated from the underlying equation. If we compare with the previous method, it shows the more accurate result, similar to the ground truth. So, our new method DVGA significantly outperforms the previous WSG, the basis of the Gaussian approximation, and EGA in terms of the sum accuracy. And then to quantify the accuracy with some well-known measure, they calculated the pullback divergence between two probability distributions. So by its definition, when the approximated probability distribution and real probability distribution is similar, the long term close to the 1, so the value of the perfect divergence decreases. So low perfect divergence is the accurate approximation. Then, as you can see in the new method DGGA, outperform compared to the other method. And similarly, relative distance, calculating the difference between the two probability distribution, also shows the more better performance in the DGGA. And then they change, and then we can change some parameters such as the noise variability or the decay rate of the variables. We can observe how the behavior of the system changes with the initial. So the result is too simple. For example, when the noise level is low, the tolerance becomes bad. It is natural as the noise level becomes high, the tolerance between the rhythms become bad. It is very natural. So there is no special result. And finally, they apply DCJ to the 44-dimensional cell cycle model. Consists very complex. So it consists of a 44-dimensional high-dimensional oscillatory system. And by applying new method, they found new page of the cell. Previously, didn't find. For example, they newly find the G phase and the M checkpoint. So dynamically, new edit point and new base. And they checked it, validated, they compared the result to the experimental data from shingles and RNA sequencing. So it shows the good alignment with the landscape generated by the data. This is the two default plane consist of two psi and psi proteins. It aligned to what with real data. So we can apply DTGA to the biological system as well. So in summary, the DTGA was the characterize the new cycle and then calculate the pre-solution by decomposing to the tangential direction and the normal direction and calculate the covariance n minus in one-dimensional covariance, merge them, and after getting the probability state, you can calculate the lattice like this, you know, fast time. So this is the summary. Thank you all.